Hello everyone, I'm Malvian and today we are going to solve the LeetCode challenge on the challenge number 110 called the balance binary tree. And for this particular challenge, it says given a binary tree, determine if it's height balance. A height balance binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than one. So in other words, we can let me visualize this by using a highlighter. The difference between each sub node is not more than one. So for example, right here we have the 3 node called the 3. We have the value of 3 and we count this by 1. But for this particular challenge, we need to recursively call from the bottom of the 3 node. So we start from the node that is null, which is from the 9, since 9 has no left and right properties, so we only returning 0 and the right one is returning 0, and the 9 is still counting 1 because it is existing with the 9 node. And also the same thing goes to 15. We have the value of 1, and 7 we have the value of 1, the value of 1 on the 7. Then after 15 we have 0 nodes or 0 value on left and right, because after 15 there is no more node. And 1 can be, after we compare these two, 1 and 1, which one has the highest value, since 15 and 7 is balanced, then we return 1. And going up to the 20, since 20 is already defined by 1, then we count this by 1, which equals to 2, using the equal sign, and we have 2. Let me mark this one and we sign this as 2. And 20 has the value of 2 or the height of 2, because 20 has the depth of 15 and 7. Then the 3 will compare both 9 and 20, since 20 has the height of 2 and 9 has the height of 1. Then we compare both to see which one is higher. Since 2 is higher, then 2 will be going up, and compares against 1. Since it is height balance with the, in other words, with the tolerance of 1, then of course 1 compare against the 2, which has the difference only by 1. So the answer is true. It's because it is still height balance. The tolerance of the height is 1. So for the other challenge, for the example number 2 right here, we have node 1, 2, 2, 3, 3, and 4, 4. Let's count this from bottom. We have 4, count this by 1, and we also have 4, count this by 1, and this one will go up. And since 3 already has 1, then of course we count this 3 with the depth of 2. And since 3 right here is already has 1 value, and there is nothing below the 3 of the sub 3 of the value of 3, then of course the 2 will be nominated and goes up to the node 2 right here. Since the 2 we already have a value of 1, then of course we count this 2 with 1 is equals to 3. Since the 2 and 1 is still returning true, it is still balanced from this sub 3, which is true, because the difference between 2 and 1 is still negligible, or it's still tolerance, because the 2 and 1 is still balanced, because the difference is no more than 1, which is also equals to 1. That is the difference. And that way this node 2 right here of this sub 3 still returning true, and this one has the value of 1. And then the total of the depth of the sub 3 of the 2, we have 3. It is because from the sub 3 of node 2 we have already as the depth or the height of 2. Then since it is already going up or went up, then of course we assign this as the value of 3. And then we compare the 3 against the 1, and 3 will go up because 3 is the highest value. Then we compare against the main root. Since 3 and 1, the difference between 3 and 1 is 2, using the math dot absolute method 3 subtracted by 1 is equals to 2, and 2 is considered unbalanced or with the height tolerance. Since the height balance tolerance is only 1, then of course since it is 2, then we have the value of unbalanced. Then the one right here, which is the main tree, we have the returning answer of false, and the output is returning false because it exceeds the tolerance, the height tolerance of 1, unlike the example number 1 right here. So for the example number 3, we have the input root equals to null since it doesn't contain any nodes whatsoever, and returning 0, then of course the output is returning true, and it is still balanced even if it's null. And we have the constraint of the number of nodes in the tree is in the range of from 0 to 5,000 range. This is the maximum number of nodes in a tree, and the constraint, it is minus 10 with the power of 4 or the exponent 4, inclusive with the node value, and 10 with the power of 4. And for the node value, we don't have to worry about this one. We only have to worry about the number of nodes inside the tree, inside the range of the tree. Okay, so without further ado, let's solve this out by checking if the difference is above 1, then return false. And we can add a check above this. If the node is null, return true or return 0. If it is a sub node or just sub tree, return 0. Like we already declared after the left and right property of the 9, since it is null, then of course we are returning 0. Then we calculate if it is already unbalanced, then signals the root node to unbalanced and just return false. We can use an algorithm called the depth first search using a function called the depth first search that takes the parameter of the node or the root node or the just node using the tree just node as the parameter. We can name this anything other than the root parameter since it is already declared root from the parent function. Since we declare inside this is balance function, then of course we can return the node instead of root because of the naming convention. Since we are using a TypeScript, if you want to use something else other than TypeScript, then go ahead, I encourage you to do so. So the TypeScript, it expects either another tree node or null, and the returning and the expected output can be a number to signal the imbalance. And for this placeholder, we can simply return false for now, since it is expecting a boolean value from the return is balance function. And for the depth first search, we can check if node, like I already declared from after the 9 or the 15 of the left and right property, using the left and right property of the sub tree node. If it is null, then of course we are return 0. We check if the first node is equals to null, then we return true or return 0, and it is still signals balance because it is not being counted of the tree node. If it has the node, then of course we are returning 1. We can return 1, but before that we need to check if it is unbalanced or not. Since this one is already balanced we have the height of 2, and after this one on the node 2 right here of the subtree, we have the height of 3, and then compare against the 2, we have the 3, and we'll go up and we can check 3 minus 1, or the difference between 3 and 1 is equals to 2. Since it is 2, then of course we signals imbalance because the tolerance is only 1. Since it is the height difference is above 1, then of course we can simply check if using the math absolute check if left node either left node or the right node is above 1, then of course we return -1 to signal the imbalance, like we already described from this kind of node. We have the height of 2 from the node 3, and we have the height of 3 with the node 2. Then we compare the 1 against the 2. Since the difference is 2, the height difference is 2, then we are returning -1. Check if it is imbalanced by checking the difference above 1, the height or weight difference by 1. And since we already declared the left node and the right node to check between the left and right property, then we can assign the node using the left node, store the value from the bottom. Since we're counting from the bottom using the recursive call, check using the depth first search, recursively calls the depth first search again, call the node.left. And the same thing goes to the right. Yes, you guess it, using the right node, using the DFS again, DFS node.right. And we take the left and right property from the node parameter and store the value from the either left or right node to check if it is imbalanced using the if else with the absolute method. The absolute method using the difference right here. We have the Math.abs method using the a minus b to check the difference between 3 and 5. Since 3 and 5 from the math absolute, we have the value of -2. Since we are using the math absolute, then the -2 of the negative sign will be ignored. That notation of the negative notation will be ignored. Then of course we only return the positive because we are counting the difference. What about we calculate between 1 and 2? Then of course we got 1. We have the difference of 1. What about we count the 1 with 10? The difference will be 9. We can place the 10 on the left or we can place the 10 on the right. It is still counting as 9. That is the one need function to be utilized. Okay, so let's go back to our implementation to check. Since left node, as we declare right here, we have 4 and 4. We have the value of 1. Both 1 will be counted up to the 3. We have the value of 2. We have the total height of 2. And then compare against the 3. Since 2 and we have the 3 with depth of 1, just 1. Then we compare the both 2 and 1. And 2 will be nominated and compare with the 2 right here, and we calculate the store and we calculate the 2 and 1. We have the depth of 3 or the height of 3. Then we store the 3 right here besides the node 2. So don't forget to use the return 1 with the Math.max to check which one of the from the left and right node to see which one has the highest value using the left node or the right node. And we store this one to check. Since it is both 1, then we store 1 upward and then counting by returning 1, and we have the value of 2 and 2 with 1. Since 2 is higher using the Math.max right here, from the left node is higher, then of course we add the 1 upwards and we got 3. Then to check again with 2, since with 2 has the depth of 1 and it is depth of 3, then of course it is catched by the math absolute check. The left node and right node has the difference of 2. Since it is highest or higher than 1 difference, height difference, then of course we are returning 1, signaling that it is already false, it is already imbalanced. Then for the return, we can check the false value or the false statement will only triggers using the DFS, call the DFS with the root as the parameter. We are passing the isBalance root parameter to the DFS with the parameter of root, and we convert the root into our node to be processed by the DFS function. And we can add a check to triggers if it's either false or true using the height difference of -1. If it is returning -1, it is already catched by this early check. Since it is returning -1, then the DFS root will returns -1. Since -1 is equals to -1, and we are returning false because the comparison or the notation is not equals to -1. And in other words, we need to check. We can still returning true as long as it is not equals to -1. If it is -1, then we are returning false. If it is something else other than -1, then we will return true. And because it is from the isBalance function. Let's say we have -1, then it will return false. If we have the 0, since 0 is not -1, then of course we are returning true because it is still balanced. And we can add another early check to check if the left node from the recursive check from the bottom, if it is already signals -1 from the bottom, then of course we can add a check if the left node is equals -1. If it is equals -1, then of course we are returning -1. The same thing goes to the right node. Check if the right node is equals to -1, then of course we are returning -1. And these are for early check. If it is already imbalance from the bottom that goes up, then we don't have to count everything from between the left and right property, and we just returning -1 up to the point to the root node. So before we store the value, we need to add an early check, early catch after we counting the left node using the DFS call again, and then the right node using the DFS call again, without waiting. If either the left node and right node completes computing the DFS recursive call, then we can catch early from either the left and right node. Then we can add a gateway. If the left node is already imbalanced, then of course we only return early without waiting from this right node calculation. So it looks good. Let's see if it works. Using the checking the code, it is accepted. Okay, so let's run the code. Submitting using the Control Enter to see if it works. And we have the runtime of 1 millisecond. So it looks good. Okay, so that's about it. I hope you understand my explanation. If you still don't understand, you can ask me in the comment section. Or if you have any better solutions regarding this challenge, tell us what you think in the comment section. I hope you have a great day. Thank you for watching the video, and I will see you in the next video. Goodbye.